Canberra is required
Okay,
or
okay.
is it not? Uh,
We now proceed
Optional.
to session 3 of the day 6. To begin today's next session, it's my honor to introduce our next speaker, Dr. Vamsi Krishna Velidi, scientist, engineer, SF, UR Rao Satellite Center, Indian Space Research Organization, that is ISRO, Bangalore. Dr. Vamsi Krishna Velidi received the MTech and PhD degrees in RF and microwave engineering from Department of E and ECE from the IIT Kharagpur in 2008 and 12 respectively. In 2011, he joined the ISRO UR Rao Satellite Center, Bangalore, as an engineer in the Communication System Group, where he is working on the design and development of high performance compact microwave passive components for various spacecraft communication systems in Indian remote sensing, geostationary, interplanetary, and scientific missions. He is Deputy Project Director, PTC RF Systems for Communication Satellite, GSAT N3. He served as Project Manager for Remote Sensing Satellite Missions, that is NISAR, XPO SAT, RISAT, 2B, R1, R2, and last one HYSIS. He has co-authored 72 papers in international journals and conferences, including 36 in peer-reviewed international journals. He served as the editor board member from 2015 to 2017 for the Wiley International Journal of RF and Microwave Computer Aided Engineering and has been serving in the review board of various international journals. He is the recipient of the ISRO AISI Young Scientist Award from Astronomical Society of India in 2016 and the URSI RCRS 2017 Young Scientist Award from International Union of Radio Science. He is also a recipient of the ISRO Team Excellence Award 2017 for his contribution in the design of compact microwave filters for NAVIC and NAVIC SPS. His current research interests include design and characterization of high-performance microwave passive components using planar waveguide, substrate integrated waveguide, and semiconductor technologies. Sir, we are delighted to have you. I invite Dr. Vamsi Krishna Velidi to continue with session 3 of day 6. Sir, the stage is
Yeah,
yours.
yeah. Thank you very much for the introduction. So I'm sharing
Thank you,
my
sir.
presentation. So good afternoon all. So please confirm whether the
Very good afternoon, sir.
screen is visible to all.
Yes, sir. Screen is visible.
Yeah. So shall I proceed?
Yes, sir. You can
Yeah,
proceed.
yeah, yeah. So good afternoon once again. So here in this session, I would like to cover the design of high performance and compact RF and microwave filters for this spacecraft and as well as other wireless applications. So since the filter design is a vast topic, so I'd like to cover the transmission line based design. Particularly, this is aimed for that faculty who are interested in RF and microwave engineering, particularly, and using the circuit design with mostly we are using for antennas and other microwave devices. We are using the high frequency EM simulators. So, in addition to that design of electromagnetic simulators, first the basic understanding of the circuit is very much essential. So, if we are able to design and if we get the knowledge of the any passive component or any transmission line element, so that we can construct the filter using the transmission lines as a building block. So, this gives for the student or any researcher a proper understanding for his future developments. So, instead of using directly that electromagnetic simulators as a structure oriented design and simulating and rather later understanding the uh, principle of operation. Instead of that, if we have proper circuit design from the beginning itself, it is very much it is very useful for the proper understanding for the future research. So that's why here, particularly in this FDP program, so whatever we have so far we came across for the different applications and how a particular specification can be targeted with the knowledge of the filters. So the process is how our journey started, what is our understanding, what are the motivations behind, and what are the difficulties faced. These I would like to cover in this session. So I hope this will be very much useful and give some more interest for the new beginners, uh, or you can encourage more people into RF and micro engineering. So coming into the point, the objective is to design now the entire world is going for miniaturization and at the same time weight and cost reduction. So for that, since we are in the application field of space industry, now we target mostly space applications and also the other applications will be covered. Now, the design should be easy to realize and smaller in size, and it should have uh, uh, multiple characteristics like it, compared to the previous designs. It should have superior characteristics and multiple frequency of operations like dual band, tri band. These are the design challenges for the new era. So like ultra wideband, wireless LAN, and IoT, and further 6G, 5G, and above application. So we should always think one step ahead to meet the future requirements. Now, as we know, the most of the articles related to this particular design can be found in this IEEE first micro Ethereum technique. Earlier it is micro wireless component, now it is wireless technology letter and micro magazines, electronic letters. And from the Wiley, it is these are the just top journals covered here. There are so many other journals also. At this now the important textbooks also just I want to show here. Basically, for proper understanding the best a good startup is micro engineering by Quasar and my colleague and other circuit design and particular to microstrip filters. Today's topic for the RF and microwave applications, all different variety filter configurations, filter topologies for different applications are well covered in this JS handbook. Now, today's outline. So, just to give the introduction to passive component, not only filter, there are other passive components also because these filters can be used for their applications also for size reduction purpose. That's why we'll give a brief introduction. And what is the workflow? How to from the design to final fabrication and measurement? What is the design flow? And here mostly for the understanding, we'll highlight the transmission line units as a building blocks for the filter design. In this band stop filters, low pass filter, dual band design, because it's difficult to cover everything in one session. I'll try to give more emphasis on variety of application and all variety of filters also. And at the same time, applications will cover for antenna design that is called the filtering antennas. Nowadays, filter integrated antennas are called filtering antennas. When the I mean, instead of using antenna and filter are separate components, if you are able to integrate them, or if you are able to design together, so that is also interest. And the diplexer is the most common application, particular to space application that I want to highlight this. And at the same time, couplers and balance also. So since their uh, structure point of view, they are very large in size. And also using these filters, we can miniaturize those components to have better performance with harmonic suppression characteristics. That I will highlight. So these are just here most of the designs we can now realize in planar technologies. There are other technologies like waveguide technologies, coaxial medium, and at the same time now recently substrate integrated waveguide technology is there, and LTCC technology is there. Then for a student immediately easy to realize practically is planar technology, microstrip and strip planar and coplanar waveguide technology. because within short time, the turnaround time also very small to realize the component and immediately verify the component. Since these components can be, though other technologies are available, these are always evergreen with microchip and discipline based design, because they are very easy to integrate with the other circuits. And at the same time, the performance is moderate compared to wavegates. Nowadays, with new technologies, the performance are on par with wavegate designs also. They are competing. But anyway, each technology is having its own advantages and limitations. Now, the particular application for any communication system is a transmitter and a receiver and antenna we have. These are the three major areas in any communication system, whatever may be the application. Like, for example, satellite communication, if you have for telemetry tracking, immediately once the satellite is launched, to get the details about the satellite, whether it is in proper orbit, whether other parameters are details like temperature and other thermal, all details are, we call it as telemetry. Those information we should communicate to the Earth. So then only the satellite will be placed properly in the required orbit. At the same time, its health condition, where how it is, other parameters are performing well or not. So communication is very much essential. In that, mostly the transmitter will be there on the satellite. It is called onboard transmitter. At the same time, whatever we are commanding from the ground, one receiver will be there. And at the same time, antennas are very important. So that's why this application is called telemetry tracking and command. At the same time, when the satellite collects some data, that entire huge data to be transmitted to the ground with the help of communication system only through the antenna. So that is called data transmitter. Now, as the frequency increases, earlier we started our communication from VHF, UHF bands to now it moved to L band, S band, X band. Now Ka band is the frequency of operation to send huge amount of data. So whatever may be the application, whether it is navigation or data transmission or telemetry tracking and command, the essential components are transmitters, receivers, and antennas. So coming to the transmitters, if we see the baseband, the data signal is modulated, and after that it is amplified and it is sent through the antenna. In the intermediate stages, we'll have some spurious components due to nonlinearity of amplifiers and other oscillators. So the filters are very much very important components to suppress those unwanted harmonics and other interfering signals. So in every stage, depending on the requirement only, filters are very much essential. So coming to the receiver, since the signal travels in the free space through long distances, so immediately the antenna should not receive a wideband noise. So whatever the particular frequency, that pre-selection should be very important for a receiver. So immediately after the antenna, that's a pre-select filter will be there that allows only the particular band of interest, and it will reject other band. Suppose if the transmitter is also nearby to the receiver, we should reject the high emissions from the transmit signal also. Otherwise, the receiver gets saturation. That's why the pre-selection operation using the filter, without the filter, the receiver gets saturation. So entire system will be of in difficult state. So filters are very much essential component. Suppose once that pre-selection is done, then after that, after low noise amplifier, we'll have image of that frequency that can be that also to be rejected. That is called image reject filter. So at after LNA, after mixer, uh, so before mixing itself, one filter is required, and mixer consisting of again amplifier, sorry, uh, tra- non-linear devices. So that's why that harmonics and unwanted sequences are to be rejected and clean signal to be given to the next stage. So in every stage, the first down conversion. In the first mixer, that RF signal will be down converted to almost in the 400 megahertz. Suppose it is in S band, the receiver signal is about 2 gigahertz. Suppose in the first down conversion, it will be converted to come in 400 megahertz like that. Then finally, in the second down conversion, gets converted to 990 megahertz or 20 megahertz. Finally, the baseband signal will be extracted from the carrier. So in this Almost in every stages in the receiver, filters are required. At the same time, in transmitter. Now, the present research is integrated filters with the antennas also. So that's why in transmitter and receiver and antennas, these filters are becoming integral part of the design. And multiplexers and diplexers, those also special applications that I will show in this particular place. Now, just coming to other passive components, there are 90-degree and 180-degree couplers because there must be an power division. Suppose in any amplifier sizes, suppose 100 watts we are not able to achieve using a single device, we'll use some 3 4 devices to combine, so that there the power division is required. And suppose in the communication system, some 2 3 paths are there. Suppose one high power is to be transmitted and some low power is to be tested, then one small coupler will be used. So in that way, for different applications, suppose two transmitters are to be connected, then we'll use one 3 dB coupler. That means suppose for main transmitter and one redundant transmitter if you are using. For every satellite, almost we'll have a redundant, one spare transmitter and receiver. So suppose one fails, we'll use the another one. In that way, to divide the power, so there will be a requirement for equal power division and unequal power division. And sometimes in spaced array antennas, there will be a huge requirement of these couplers to provide a particular phase to each arrayed element, 0 degree, 90 degree, 180 degree, 2 degree, like. But however, these components also can be constructed using the transmission line, but the overall size is very large. Suppose if it is in S band itself or L band, that quarter wavelength line of each will occupy larger size. And also these couplers also in turn will produce harmonics in the out of band. These to be rejected, so that's why these filters can be used to reduce the size of these couplers and to suppress the out of band harmonics. And there is another one called balun. Balun is also very essential component for a dipole antenna to feed, and for also some, now all the receiver circuits, transmit circuits are coming in differential form. We need to feed power. So for the differential circuits also in the input side, balun is required. Balun is nothing but it will provide two equal amplitude signals but with opposite phase. So it is called unbalanced signal to balanced conversion. That's all. So this is also having huge advantages. For this also, to reduce the size, we are using filters. Now quickly I'll just show the difference between the high performance filter versus earlier traditional conventional filters. Here for the band stop filter, one example, this is shown as a stop band here. This is the ideal response, but practically none of the filters will have ideal characteristics. There is a traditional method using conventional lambda by 4 shunt open stubs. Each shunt open stub will produce a stop band. It depends its impedance and all. The characteristic stop band will be of this gradual slope it is having. So it is not as sharp as the ideal filter. And if you see the out of band, suppose this is designed at operating frequency 1 GHz. If you see the out of band, then the same response will get repeated at odd multiples of the operating frequency. These are called harmonics. Then what about the high performance filters, for example? So instead of having one stop band, if you provide multiple transmission zeros in the stop band, then the pass band to stop band transition becomes sharper than the conventional design. So this we call little high performance filter. The moment this left transmission zero is as close to as pass band, then the sharper is the pass band to sharp band transition. And these filters also may have harmonics. That is just to show the out of band response on the harmonics. Then what is required is, uh, I'll say, then suppose this is a low pass filter, it should have pass band to stop band very sharp cutoff here. But traditional filters will have a gradual cutoff. And depending on the size of the filter, if you increase the order of the filter, then only the sharpness increases. Suppose if you are able to achieve very sharp characteristic with smaller size, that is of great interest. So here in the second plot, it is shown as one pass band to stop band transition is bit sharper, and the stop band extended up to very large extent. So now these type of filters are of great interest. So earlier band stop filter, if you see, if you are able to suppress this harmonic, then the band stop filter can be called as a low pass filter with wide stop band. So that means we are able to suppress the harmonics of the band stop filter. It will become a low pass filter with very wide stop band. This will have very good applications in antenna harmonic suppression as well as other modulator harmonic suppression to wide extent. So these filters are very much essential for the transmitter output stages for any communication system. And coming to the dual band filters, a single component, suppose instead of using two filters to get two frequency response, if you are able to get this uh, two responses simultaneously using a single unit, that is of great interest here. So earlier in the conventional method is to use two filters combined together to get the two bands. But now there are methods to provide a single transmission unit which produces automatically two bands. Now these two bands are not to be confused with the harmonic. If you see the set, the first two bands are called one set. The entire set will repeat as a harmonic if you see the out of band. So harmonics are not the multiple bands like earlier way. These are at odd multiples. So if you see the first set at 1 gigahertz, if you see passband behavior, two stop bands just left and right, the same set is getting repeated. So this is dual band stop. Similarly, dual band pass also can be seen. Now coming to the band pass filters. So band pass, we know a particular band is getting transmitted, and other out of bands are to be rejected. But conventional designs will have again a gradual passband to stop band to passband transition, and this will also have harmony. Now here in the second plot, if you are able to produce a transmission zero, then the moment if the transmission zero is controllable, if it is moved towards the passband edge, then the sharpness increases. So the same passband again getting repeated as a harmonic here. So these are the just examples to show how we are getting closer to the ideal response. Ideal response is the best reference. So that's why whatever a designer is saying that filter is having very good sharp rejection characteristic, then that means it is as closer to ideal. And how it is achieved is important. So if you are able to design with smaller size instead of increasing the filter order, that will in turn increase the filter loss. So all are interdependent. If you are able to achieve with low loss and sharp rejection with a small size, then that design is going to be the best one. So that will lead to the next research actually, that research interest. And coming to the dual band pass response. See here in the first pass band and second pass band, and immediately after the pass band there are stop band. Here the rejection level is only 10 dB. If this could be increased to 20-30 dB, that is also a great interest. So the researchers who are in the filter design can not only concentrate on the dual bands, they can also concentrate on the out of band rejection levels and how narrower the pass bands. And there must be a very good isolation between the two pass bands. Here simply one transmission zero is created, but suppose here also two more transmission zeros are created, and that will also be a important parameter. That means pass band to pass band isolation, how well they are getting separated. Now, if you see the harmony, the entire set of the two pass bands are getting repeated or odd multiple. So earlier one is dual band stop. This is dual band pass. Now coming to the hybrid couplers, just to quickly I'll show. uh, This is 180-degree hybrid coupler, which is constructed using six quarter length transmission lines. So it will produce two outputs at port 2 and 3 if you are giving power at port 1. So port 4 will be isolated. So six quarter length transformers will occupy a very larger size. So, and the coupler response at operating frequency will be like this. That means 3 dB at the operating frequency in the output, and isolation is around 40 dB, and return loss also to be 40, 30, 40 dB of the order. And if you see the out of band, the harmonics are getting repeated. Now, the research interest is to suppress those harmonics. Here, some method is applied that is not shown here. The response of the high performance coupler is shown here. Only at the operating frequency that characteristics should be there, fully out of line, all harmonics are to be suppressed. If the suppression level is also 20-30 dB, that is also a great interest as a research objective that is also. Now the how to design this component. So first the micro passive circuit, whether it is filter or coupler, we'll see. Then the statement, what has to be, allow the specifications. What should be the, if it is filter, what is the frequency band, and what are the pass band parameters, and where to be, what is to be rejected and all. And for this, we'll have some proper knowledge, just conventional methods or existing some methods. If you see, you will get some more information, novel idea. Based on that, you can have some combination. That is the now research idea. That's all. So the novel configuration you can also propose or you can try. So for that, we should develop a theoretical analysis first. So for this transmission line theory, understanding is required. Then you can using the simulation without using EM simulator. So far, that means you can derive its S parameters based on the transmission line analysis, so that you can simulate entire parameters. You can give in MATLAB, so that you will get the output response. And later on, if you are satisfied with the design, then only you will go for implementation using microchip. So far, whether it is microchip or waveguide, we are not bothered. So we are fully up to the half of the design. We are in theoretical analysis only. And once we implement, then whether waveguide or microchip, then we'll implement in the form of a structure, its physical structure. Then that optimization we can have. Then EM simulation will consider all losses and all. In the theoretical analysis, the ideal response will come. That is our reference. So if you are implementing in planar technology, you can have different choice of substrates. And if it is in waveguide, the medium, if it is the electric field or normal waveguide, air field, that we will consider. And once that, considering all electromagnetic effects into account, then you will proceed for EM simulation. Once the results are, you compare with the circuit simulation results. Once you are satisfied, those are an almost good agreement, then finally you will go for fabrication. So instead of wasting several units in a hit and trial method, if you have proper way of approach, then the first cut itself will have measured results closely meeting to the circuit level. Now just also transmission line building blocks as a building block for a filter. Earlier traditional method, theoretical methods are using different methods of the filter design, like image parameter method. It all can be seen in POSAR or any other Jay's Hong book. But now these methods we are not at all using. But just to give an idea how traditional filters are designed, the responses we should have knowledge, like whether it is Chebyshev or maximally flat or elliptic function. That means suppose the response will correlate with what kind of filter you are designing. That means in the present scenario, what we need is all elliptic filter response only or quasi elliptic response only. That means the pass band to stop band transition is very sharp. That is the only thing. Earlier, before that, there is a Chebyshev response. That means it will have higher rejections and ripples in the stop band. And maximal flat is insertion loss is very less. But pass band to transition, stop band transition is gradual. Only thing, by just increasing the filter order only, we are able to achieve the sharp reduction. And earlier filter methods, first a low pass prototype is to be designed, then it is to be converted into band pass or band stop using different methods proposed. So that was the traditional approach. Now what is the uh, transmission line based design is now we are entering. A simple transmission line is characterized with impedance and electrical length here. So just to have an idea between the electrical length and physical length, the theta is equal to beta integral. Beta is the wave number. So 2 pi by lambda. If the length of the line is to be lambda by 4, then electrical length is in this one 90 degree. If it is lambda by 2, the electrical length is 180 degree. Just this degree we are using easily instead of mentioning in the physical side. Yes, or one other directly also you can mention in terms of lambdas also. The input impedance expression is given here. A transmission line is loaded with ZL. The relation between load impedance and characteristic impedance and input impedance is this one. Now, what are the prerequisite knowledge for the filter designing? To have micro network theory, uh, we should have some knowledge. That means the different parameters to represent a two-port network. That means the two-port network is having input impedance and output. It will be loaded. For example, this is a filter or any uh, amplifier. So there it is a two-port network. Basically, most of our designs are two-port networks. Once two-port network analysis is understood, then we can apply to multi-port networks also. So that's why to represent any two-port network, we have different parameters: impedance matrix, admittance matrix, ABCD matrix. Suppose two-port networks are connected in series, then we can use impedance matrix to analyze that one. Or if two are connected in shunt, we can have admittance matrix to get the overall parameters. Or if different two-port networks are connected one after one, that is called cascading. Then ABCD parameters are very much easy to analyze the overall parameters. So that I think. Now finally, whatever may be the parameters, because the measurement device what we have in our lab is vector network analyzer, which will give the S parameter. So finally, we'll convert the all parameters into S parameters. So we should have finally S parameters notation also uh, uh, some understanding. So basically for two-port network, that S11, 12, 21, 22 are very important. In this insertion loss, that is S21. So and return loss are the important parameters. Mostly we are expressing in dB only. Now for different circuits, there are already derived ABCD parameters here. Suppose a series element, ABCD parameters are like this, shunt element G, simple transmission line of having here length also you can say theta instead of beta. So beta L is the electrical length here everywhere. Z characteristic impedance. If it is a pi type network represented with Z, and if it is a T type network, these are all just ready-madely derived things just shown here. And suppose whatever may be the parameters you came across, finally the conversion from one to one, S to Z and Z to ABCD or ABCD to Z, all are we have already uh, ready-made available expressions here. Now, what are the different transmission line elements? A simple transmission line element already I have shown, and a open stub unit here. That means output of the, I mean, one end is open, and if it one end is shorted, and it is called double section or stepped impedance. It is called. That means if the impedance are same, it is called uniform impedance line. If different impedance, Z1 also and different Z2, then it is called stepped impedance. And in addition to that, there are several transmissions. Those are called coupled lines. These are very much useful in design of band pass filter. These simple transmission lines and double section